Welcome to our deep dive into the chemistry of nebulae, those cosmic clouds of creation. We're going to break down 5 key facts that I think are going to change how you see these incredible stellar nurseries.
I'm excited to dive in. Most people just picture nebulae as these gorgeous, colorful clouds, but there's so much more to them than meets the eye.
Right, it's like space chemistry. What even is that?
It's surprisingly similar to chemistry here on Earth, just on a much grander scale. We're talking about the interactions of elements like hydrogen gas dust grains and even more complex molecules, all swirling around in these massive cosmic clouds.
So let's start with the basics, hydrogen gas. It's kind of a big deal in nebulae, right?
Absolutely. Hydrogen is the most abundant element in the universe, and it's the primary component of nebulae. Think of it as the foundation upon which everything else is built.
Okay, so hydrogen is like the basic building block. But what about those dust grains? They always look so mesmerizing in pictures.
They're more than just pretty dust. Dust grains play a crucial role in nebula chemistry. They're made up of things like silicates, carbon compounds, and even ice particles.
Wait, hold on, ice in space.
It sounds counterintuitive, but in the cold, dense regions of a nebula, molecules can freeze onto those dust grains, forming a kind of cosmic frost. And those tiny ice particles can hold a surprising amount of information about the nebula's history.
Okay, so we've got hydrogen gas as the main ingredient, and then all these fascinating dust grains mixed in. What happens next in this cosmic recipe?
Well, that's where things get really exciting. Gravity starts to pull all that hydrogen gas and dust together, forming clumps that get denser and denser over time.
And I'm guessing those clumps eventually become stars.
Exactly. As those clumps collapse, the core gets so hot and dense that nuclear fusion ignites, and boom, a star is born.
Wow, so all that from just clouds of gas and dust. It's incredible to think about. But I have to ask, what about those complex molecules you mentioned earlier? What role do they play in all of this?
That's where we start getting into the really mind-blowing stuff. Some nebulae are incredibly rich in complex organic molecules. We're talking alcohols, aldehydes, and even amino acids, the building blocks of proteins.
Hold on, amino acids, those are found in living things here on Earth, right?
That's right. It seems these building blocks of life aren't unique to our planet. They're found out there in the vast expanse of space, forming through complex chemical reactions in the gas and on the surfaces of those dust grains.
So it's not just about star formation, it's about the potential for life itself. It's a lot to take in.
It is, and we've only just scratched the surface. There's so much more to unpack about these fascinating cosmic clouds of creation.
Well, on that note, maybe we should pause here and let our listeners digest all this incredible information. But don't go anywhere because we'll be back soon to delve even deeper into the chemistry of nebulae.
Welcome back to our deep dive. I'm eager to unpack even more about these nebulae with you.
Me too. It's kind of blown my mind that we're finding the building blocks of life like amino acids just floating around in space.
It really challenges our perspective on the universe, doesn't it? And it raises some fascinating questions about the possibility of life elsewhere. But before we get too far ahead of ourselves, let's talk about how those clouds of gas and dust actually become stars and planets.
Okay, back to the basics then. So we've got these giant clouds of hydrogen gas and dust. How do we go from that to a structured solar system with planets and moons and everything?
It's a complex dance between gravity rotation and a process called accretion.
Accretion. That sounds intense.
It's actually a pretty straightforward concept. Think of it as cosmic clumping. Smaller particles like those dust grains we talked about collide and stick together under the influence of gravity. Over time, those clumps grow larger and larger, attracting even more material.
So it's like a snowball effect in space.
Exactly. Now imagine that snowball swirling around a newly formed star. As it orbits, it continues to pull in more gas, dust, and ice, eventually forming planets and moons.
So our entire solar system, with all its diverse planets, asteroids, and comets, is basically the result of accretion in a nebula billions of years ago.
That's right. The chemical composition of that original nebula determined what kinds of planets could form and where they ended up.
That makes me wonder, if different nebulae have different chemical makeups, could there be planets out there made of things we can't even imagine?
Absolutely. We're already discovering planets orbiting other stars that are wildly different from anything in our solar system. Some might be made of incredibly dense materials like diamond planets, while others could have oceans of liquid methane.
Diamond planets. Okay, now I am picturing myself on a spaceship. But seriously, is it possible that there are planets out there so different from Earth that we haven't even conceived of them yet?
It's not just possible, it's highly probable. The universe is vast and full of surprises. There could be planets with atmospheres so thick they crush everything on the surface, or planets that orbit multiple stars at once.
Multiple suns. Wow, that would make for some interesting sunsets.
It really highlights the incredible diversity of planetary systems that can arise from the chemistry of nebulae. And the more we explore, the more we realize how much we still don't know.
It makes our little corner of the universe seem even smaller.
True, but it also highlights the interconnectedness of everything. The atoms in our bodies, the air we breathe, the earth beneath our feet. It all came from a nebula billions of years ago. We are quite literally stardust.
That's beautiful and a little bit mind-blowing. So we've covered how stars and planets form from nebulae. What else do we need to know about these cosmic clouds of creation?
Well, we haven't even talked about the amazing variety of nebulae themselves. There are emission nebulae, reflection nebulae, planetary nebulae, each with its own unique characteristics and chemical signature.
Okay, I'm definitely intrigued, but I think we're out of time for this segment.
Indeed. We'll have to save our exploration of those fascinating nebula types for the grand finale.
Sounds good. We'll be right back to wrap up our deep dive into the chemistry of nebulae. Don't go anywhere.
Well, then let's start with the showstoppers emission nebulae. They're the ones that really grab your attention in those stunning space photos glowing with vibrant reds, blues, and greens.
Like giant cosmic firework displays. What makes them so colorful?
It's all about the interplay between the nebula's gas and the hot young stars born within them. Those stars blast out intense ultraviolet radiation, and that energy excites the hydrogen atoms in the nebula.
So it's kind of like a cosmic black light making things glow.
That's a great analogy. When those energized hydrogen atoms settle back down, they release that extra energy as light, and that's what creates those brilliant colors.
That makes sense. So what about reflection nebulae? They sound similar.
They are related to starlight, but instead of emitting their own light, they're reflecting it. Think of shining a flashlight on a dusty mirror.
You'd see the beam scattered by all those dust particles.
Exactly. Reflection nebulae tend to hang out with younger stars and often appear bluish because the dust is better at scattering blue light than other colors.
So emission nebulae are like glowing gas clouds, and reflection nebulae are like cosmic dust bunnies reflecting starlight. Okay, I think I'm getting the hang of this. What's next?
Now we move on to something even more dramatic, planetary nebulae. Don't let the name fool you, though. They have nothing to do with planets. They form when a star, much like our own sun, reaches the end of its life.
Okay, now that sounds interesting. What happens to the star?
As the star runs out of fuel, it starts to shed its outer layers, and those layers drift outwards, forming a gorgeous glowing shell around the fading star.
It's like the star's final performance, a cosmic curtain call.
A very poetic way to put it, and these expanding shells can take on all sorts of fascinating shapes, ring spheres. Even hourglass figures studying their chemical composition can tell us so much about the life and death of the original star.
So planetary nebulae are like time capsules preserving a star's history, but I have a feeling supernova remnants are even more intense. Right.
You could say that. Supernova remnants are the aftermath of a star going out with a bang. Literally, when a massive star runs out of fuel, its core collapses, triggering a colossal explosion that blasts the star's material out into space.
And that creates a nebula.
It does. These nebulae are incredibly hot and energetic, expanding outwards at incredible speeds. They enrich their surroundings with heavy elements, providing the building blocks for future generations of stars and planets.
So it's a cycle of cosmic creation and destruction, all driven by the amazing chemistry of these nebulae. This deep dive has been an incredible journey.
It truly showcases how the smallest scales of atoms and molecules connect to the grandest scales of stars and galaxies.
We started with simple hydrogen gas and dust, and now we're talking about the life and death of stars, the potential for life on other planets, and the very elements that make up our bodies. It's mind-blowing.
And the most exciting part is that we're only just beginning to understand these cosmic clouds of creation. There's still so much more to discover out there.
That's a great reminder to keep looking up and exploring the wonders of the universe. Thanks for joining me on this deep dive.
It was my pleasure. Until next time, keep those questions coming.